Creo que estamos casi listos para empezar. Todo lo que nos pudieran acompañar, cambiamos de día. Espero que no haya sido muy complicado de miércoles a jueves. Pero lo hacemos por una razón especial. Hoy tenemos a una persona que nos acompaña desde Carnegie Mellon. Él es Senior Research para el Departamento de Data Science for Social Good, donde utiliza lo que normalmente platicamos aquí, que vemos temas de Machine Learning, Data Science, pero sobre todo con un impacto social y de política pública. Entonces va a ser una charla muy interesante de cómo aplicar técnicas de Machine Learning para prevención de, en inglés como se conoce como homelessness, en español pues, normalmente personas sin hogar, ¿no? Entonces, pues ya vamos a empezar con él. Antes de presentarlo, solo quería preguntar, ¿alguien es nuevo aquí? ¿Es la primera vez que nos acompaña? ¿Levantar? ¿Bien? Okay. Los demás ya han venido algunas veces. Y bueno, la idea siempre de este espacio es tener algunas charlas, traer a invitados, traer a gente, pero sobre todo es hacer comunidad, ¿sí? La idea que hemos tenido desde el principio es hacer una comunidad de ciencia de datos aquí en México, sobre todo en Ciudad de México, donde podamos conocer quiénes están estudiando. Antes era muy difícil tener esa apertura, esa conexión. La idea es que pasen aquí un rato, tengamos una charla y que al final tengamos una sesión de networking también, que se conozcan los que son nuevos también. Acérquense con las personas que llevan buen rato aquí. Hemos visto personas salir con propuestas de empleo, propuestas de investigación, etcétera. De eso se trata realmente este espacio, ¿sí? Lo hacemos todos los meses, tratamos de hacerlo todos los meses, ya llevamos una buena racha de lograrlo. Y pues ojalá nos puedan acompañar a las siguientes charlas. Las próximas charlas también vamos, los próximos 2 meses, a traer invitados del extranjero también, que van a presentar algunos proyectos interesantes como el de Casun, y pues espero lo disfruten. Muchas gracias. Casun.
Thank you. Gracias, Carl. Sorry, I don't speak any Spanish, unfortunately, so I'll have to do the talk in English. So yeah, my name is Kasun Amarasinghe. As he mentioned, I'm a research scientist with Carnegie Mellon University, working in the group of data science for social good. A bit about me, I'm originally from Sri Lanka, which is a tiny island south of India in the Indian Ocean. Did my undergraduate studies over there, got my BSc in computer science, and then moved to the United States for my graduate school. And that was in Virginia, and then moved to Pittsburgh and joined Raid Ghani's lab in doing data science, machine learning for social good stuff. So my background is in completely computer science, machine learning, pretty boring, not super multidisciplinary there. So hopefully this talk, this particular problem might not be super relatable to a Mexican context, but the problem template that we come across here is transferable to many different policy domains, and not just policy domains, but other decision-making systems as well, where you have a limited resource, so different avenues to serve them. How do you target your limited resources to optimally get the most out of it? So that's the problem template. Hopefully the general lessons that we draw out from this will be applicable, even if the problem context itself is not super relatable to you. Quick word about the team. I get to work with some wonderful people at CMU. Professor Raid Ghani is the director of the group. He has been one of the pioneers in the field of using machine learning and data science for public policy and social good. He was at University of Chicago before, and he started this summer fellowship called Data Science for Social Good that brought together students from around the world to work on impactful problems with nonprofits and governments. And that's where I met him. I was lucky to be a part of that fellowship in 2019, and I met him and ended up joining his team after that. Alice, Lily, you might know already. Jesus Ramos, or Chucho, as most people know him. That's his wife, and I think Lily's going to be speaking to you all in the next month as a part of this event. So we sit in the intersection of machine learning department at School of Computer Science and the School of Public Policy. So we have one foot across the two departments. And our work is mainly in applying data science and machine learning in collaboration with nonprofit organizations or government organizations to optimize decision-making systems to maximize output. This project that I'm going to talk about started as a part of the Data Science for Social Good Summer Fellowship that happened in 2022. I was lucky to be a part of that team in the periphery, but the fellows, the students who were working on this were Arun, Abby, Catalina, and Joe. They did a lot of the work upfront to get, in the 3 months, to get the project to a really good place, and then we took it over after they left it. And Adolfo was also a part of that team, whom you already know. So before we get into the project, given that the policy context might be super familiar to you, let's give me 1 second. If I talk without the mic, can you hear me? No. Okay. I will use the mic then. Nah, it's okay. I'm a little tired, so please bear with me today. It's been a long couple of days. So in the United States, housing is a big problem, especially for low-income communities. This graph that you see here is, so if you spend more than 50% of your income on housing, you are considered extremely cost burdened in terms of housing. So on the graph, the blue line is how much of the low-income population are severely cost burdened. So if you look at extremely low income, 74% of households, which is extremely low income, spend more than 50% of their income on housing. So that means you're just one shock to your system away from not being able to pay rent. And unfortunately, a lot of the low income families end up renting. They don't own property, right? And again, in the United States, it turns out to be a certain black individual, black families are more susceptible to this, given historical context. So you are just like one shock, like a health concern that you find out, or your car break down, or some financial shock. You are just like one shock away from not being able to make rent. So what happens is when you are not able to pay rent, landlords can file eviction case against you. That means file a case in court that my tenant is not paying rent to me, so I need to kick them out of my house, right? 3.6 million eviction cases gets filed in the United States on a given year. That's insanely high, right? So this is from the eviction lab at Princeton. If you want to learn more about this stuff, there's a book called Evicted by a sociologist named Matthew Desmond. Brilliant book, opened especially as someone not from the US, really learned a lot about this context through that. So this is in the whole country. Focusing on the county that I live in. So Carnegie Mellon is in Pittsburgh, Pennsylvania. The county that we belong to is called Allegheny County. And in Allegheny County, more than 12,000 eviction cases gets filed every single year. So over 1,000 on average a month, right? So you can see the shaded area on that plot here is the pandemic. During the pandemic, the federal government and state government, different levels of governments issued eviction moratoria. So stopped people from filing evictions to stop people from losing their houses. Then the cases dropped. But when the moratorium lifted, as you can see now, we are back up to pre-pandemic levels again, right? And 80% of these cases, when we look at the data, judges rule in favor of the landlord, right? So that means there's a high chance of the person losing their home. So what happens is the judge issues the judgment in favor of the landlord. Then you have like 10 days to figure out a solution with the landlord. So you can come to a settlement. If you can't come to a settlement, the landlord can apply for something called an order for possession. Then after that order for possession is issued, there's 10 days for the tenant to vacate the premises. If they don't vacate the premises, police can come and just literally throw your stuff on the street and evict you forcibly. So unfortunately, there are companies who just do these things where you take the stuff that is on the street, put them in warehouses and charge people more money for keeping those things in the warehouses. So that's a vicious cycle. So you don't have enough money to pay rent. Now you're evicted. Now your stuff is in some warehouse, and that also is accruing charges for you, right? So and these things lead to housing instability. Housing instability leads to other, like if it's a household with kids, like educational outcomes, mental health outcomes, like this. This is a spiral that leads to other horrible outcomes for people. As a plaster for this, there are public assistance programs, mainly something called rental assistance. So on the right, what you see here is a flyer that was distributed by the county government. There's a housing stabilization center in downtown Pittsburgh. If you are at risk of losing your home, you can call, or you can go in person, or you can email. You can contact them and ask for help to pay rent, financial support. And the rental assistance program exists to give temporary financial support, operative word being temporary, right? For, I think, up to 18 months of financial support to help you pay rent. During the pandemic, federal government created this emergency rental assistance program that expanded the funds that were available to rental assistance programs. I think, if I'm not mistaken, it was something on the lines of like $46 billion assigned to emergency rental assistance programs, just distributed throughout the country to keep people in their houses. So landlords will still get their rent, the government is paying that, and the tenants don't lose their homes. So this is the background context in which this project started in 2022. So the county came to us with three main questions. The Emergency Rental Assistance Program, or ERAP, was winding down. So the money that they had to give out rental assistance was going to significantly shrink. So now it's shrinking, and I think by end of this year, it's the emergency rental assistance money is all but gone. And eviction, they know eviction is a pathway to homelessness, right? So now we have limited funds. Can we use it to target and prevent homelessness? And the third one is, the current practice, as I mentioned earlier, requires tenants who are going through this terrible thing to initiate contact, either call or come in person or email or some way, initiate contact to apply for help, right? This could lead to, if someone didn't know that this service was available, they wouldn't apply for help, right? And people who sometimes need it the most don't know about the help that is available to them. So can we, rather than waiting for them to reach to us, can we proactively reach out to them? So these were the three questions. Can we target the limited resources to people who need it the most? When we talk about need, can we use that money to prevent homelessness? And three, can we do outreach rather than waiting for them to come to us? I will not go too much detail into this slide, but I put it there to illustrate how we think about approaching a data science problem in a context like this. So whenever a project is started, we do a scoping exercise. And during that scoping exercise, we fill these 5 boxes basically. We identify goals, we identify actions, we identify analysis, we identify data that is available, and all the ethical considerations that we need to think about, right? In this project, we came to three goals mainly. Overall goal is to minimize homelessness among the population of going through evictions. We have an efficiency goal. That means we need to only give money to people who actually need it because it's limited. So we want to minimize helping people who don't need the help, right? Effectiveness is, just because we help someone doesn't mean that that's going to prevent them from getting affected. So let's say someone who has a much higher need, 18 months of funding might not be sufficient to keep them stably housed for long term, right? For some people who have a temporary blip in their economic status, this temporary funding might help. So for some people, rental assistance might be necessary but not be sufficient. So can we identify people who would benefit from this the most? And the equity is, different demographic groups have different impacts on housing, right? For instance, Black individuals and Black families are disproportionately impacted by housing issues. we need to make decisions not to exacerbate those inequities. The actions here was to proactively conduct outreach and provide rental assistance funds. And to inform those actions, we needed to do two analyses. One was, can we predict who becomes homeless, right? And can we predict who would benefit from this the most? I will go through these things in detail throughout the presentation. I just wanted to illustrate that these are the things that we think about before starting a project. As before a single line of code is written, this exercise happens with the partner to figure out, okay, what are we building? What are our goals? How do we know that we've succeeded? What data do we have available? What system will we build, and how will it fit into the broader decision-making system? So basically, what we wanted to do was, the current practice is individuals apply through different touch points. And what happens is, when they apply, they are placed in a wait list, and you get prioritized based on when you arrived. So if you call first, you get served first. It's not based on the need that you have, right? So the proposed practice would be, we will conduct data analysis, do some modeling to identify people who need this help the most and benefit from it the most. And then, rather than waiting for them to call us, we will call them, right? We will go to them. So to build the ML system, and we needed to formulate the modeling problem, right? So at a high level, we know we want to predict who needs rental assistance, basically who would become homeless and who would benefit from it. We will leave the who will benefit from it question aside for now and focus on the need. Typically, when we formulate a modeling problem, we ask 5 questions. Who are we including in the analysis? So what is our universe of individuals or entities? It can be, if it's like something on buildings, for instance, then which buildings are we including? Is it every building in Mexico City, or is it one a particular neighborhood, or like who or what are we including in the analysis? What is the outcome that we are predicting, right? What are we trying to either encourage or prevent from happening? What is the output of the system? So just because we predict a certain outcome doesn't mean that is the output. It could be an output related to a single person. It could be an output related to a collection of people, right? What is the specific output from the system? What would we do with that output? And when and how often is that output generated from the ML system? So we'll start with this first question. So who's included in an analysis is tenants who are struggling to pay rent and at risk of being evicted from their homes, right? This is the universe that we are trying to help. So these are the people who are eligible for the help that we are trying. However, there's a problem. We don't know about everybody who's struggling to pay rent and are risk of eviction. The only people that we know about are people who have an evictions case filed in the court system, right? So that is a subset. There may be other people who are also struggling to pay rent, and maybe the landlords are threatening to kick them out, but we have no idea. The data only shows this. So unfortunately, we have to make that concession and update our cohort to say tenants who have an evictions case filed against them. It's important to identify that limitation, even though we can't do anything about it right now. It's good to document that, because now the county is aware, we are aware that this system would not reach that subset of the population. So we need to do something else about them, right? So being aware of that is important. That's why I highlighted that. Then the outcome that is being predicted. Ideally, what we want to predict is whether, if they are evicted, would they experience homelessness? That's what we want to predict, right? Again, limitation in the data. We don't know about everybody who becomes homeless. We don't know about people who sleep in their car, for instance. We only know about people who interact with the county's homelessness system. That's not everybody who doesn't have a stable place to sleep. And another thing, we do not know whether a person actually is evicted or not. We see a case filing, we see the judgment, we see the order for possession, but we don't see anything beyond that, right? Maybe they came to a settlement and they stayed. Maybe they were evicted without a court order, right? Maybe because landlords do that as well. So those two are limitations. So what we decided to do was, okay, we'll change the formulation. What we predict is whether someone would interact with the homelessness system at least once in 12 years after the modeling date, right? Within a year of the eviction, would they interact with the homelessness system? So if they do interact with the homeless system, we say they're at risk. If not, we say not at risk. So what's the output? The output was, now we are predicting a likelihood, a probability, not a probability, real probability, right? Some likelihood of interacting with homelessness system. The output is 100 individuals most likely to interact. Can anyone take a guess of like why it's 100 individuals? That's the resource. Yeah.
Because that's like if you had $1 million, that's the number that you decided that is enough for them to.
Exactly. It's the resource constraints, right? So we only have resources to help about 100 people. I'll get to the time frame, but that is the resource constraint. So that's where we distinguish between what the actual output and what we are predicting is.
Out of how many?
Typically, at a given point in time, there are about 4,000 evictions cases active. So it's tricky. I'll get to those nuances a little bit later, but like 100 is a general, like an approximate number that we came up with by looking at how they have helped in the past, looking at the data. But the distinction here is thinking through, okay, your model is predicting a likelihood of some event happening, but the output of the system is distinct from that. The output of the system is that list of people that we are going to outreach, right? So that's the resource constraint. So what purpose? To prioritize for rental assistance outreach. That's because we want our analysis to inform some tangible action, right? Always. If no one's going to do anything differently with this analysis, there's no point in doing this. So let's say we have this beautiful machine learning model working perfectly, but no one's using it to do anything. Nothing would change in the world, right? So that's why we highlight this. And this is where how often does the recommendations are being made? That's every month. So 100 people per month is what we're getting at. So this is the very specific machine learning problem that we're trying to solve here. So at an abstract level, I think a lot of, even when I was in school, our problem formulation would stop at, let's build a model to predict homelessness, right? So that's where we would stop the definition of model. But there are so many other details that we need to think about, especially when we're trying to deploy this in the real world, right? So this is the model that we follow to get to that very specific formulation in a problem. Okay, now we have a project scope, we have a formulation, and we'll now get to actually writing code and doing stuff. So in terms of data, we had access to the county's data warehouse. So this was a project, I think I didn't mention this. This was a project with the Allegheny County Department of Human Services. So that's a county government. So in the US, you have federal, state, and local governments. Like county government is a local government. They have a Department of Human Services. They handle all the like social subsistence, like social services stuff. And they have this expansive data warehouse. They are one of the better local government agencies in the country for having a good data system. It's relative, of course, but they have if you receive a county service, they have an identifier for you from which service you received from which date to which date. So they have that administrative record. So we had the homelessness management information system. That means captured everybody who has interacted with homelessness services in the past I think until 2012. Public housing information. So if you had received any housing subsistence in the past, that would be recorded. Any vouchers, any transitional housing, any like subsidized housing, anything would be recorded here. Any behavioral and mental health interactions that you've had with the system. If your insurance is government insurance, then that will be captured. Public benefits, other public benefits programs. I don't know whether you've heard of like SNAP, a Supplemental Nutritional Assistance Program, which is basically money to buy groceries, which is federal subsistence. Temporal financial assistance, social security, medical assistance, those programs, any interactions are recorded. We get from the court system evictions cases that gets filed on a daily basis. And also we have demographics of people. We have their past addresses collected from different touch points when they interact with the county, and all other DHS programs as well, DHS meaning Department of Human Services. So we had access to all of these systems. So we have data at a person level, service level. So this person A interacted with this service from this date to this date. And how one of the tricky things here is like matching, because they don't have, sometimes they don't have social security numbers to match. So they do matching algorithms to match people to different services. That is sometimes less than 100% reliable, but still we have a good sense of who's using which service approximately. So using all of this information, we represent a person with a bunch of numbers, basically, right? So we create features to capture a person's history relative to a certain date. Let's say we are building this model today. We create features like how many times has this person been evicted in the past? How many times has this person been homeless in the past? Any number of mental or behavioral health interactions that they've had in the past. Like these individual pieces of information, we count and create features for it. So what happens is each person at a given point in time is represented with an array of numbers. And to capture temporal trends, we calculate the same number at multiple time intervals. So number of days spent homeless in the last 6 months, number of days spent homeless in the last year, number of days spent homeless in all of history that we have. So we can have different, like how has that same entity has changed over time. So we capture that. And the last thing I mentioned a little bit, so data leakage. Who's familiar with data leakage? What data leakage is? No? Okay, so yes, can you?
So that when you are protecting your active things.
Right, exactly. So in general terms, data leakage is using data to build a model that it would not have access to at deployment time. So using information from the future to train a model in the past, right? Now when you go to deploy it, that now you won't have information from the future, right? So any information that it would not have access to at deployment time, if you use it to train, that means you're introducing data leakage. You're leaking information from the future into the past, right? So to prevent that from happening, what we do is, if we are building the model, let's say January 1st, 2022, we only use information until December 31st of 2021 to train the model. Does that make sense? I will go to an illustrative example later. Does this guarantee no leakage, or is there a problem here as well? There is a problem here as well. Unfortunately, we couldn't do anything about it at that time, because the county data warehouse has when the event happened, but it doesn't have the information about when that data was recorded. When the event was added to the database is not recorded. So we assume that event happening on January 31st of 2021 was recorded on the database and was available for modeling on the 31st itself. But in reality, it could have been a month after, right? So when you go to deployment time, let's say, what's today? I don't know, February, whatever, 27th. So February 27th, so our model thinks that events until February 26th is available. But in actuality, the event happens on February 26th, gets recorded March 26th, right? So the model expects that information, but it wouldn't have that information, right? So that is an assumption that we made that, okay, the information gets recorded on the database the same day, which is not true. But we didn't have information about when that, and different data sources have different lag times. So we couldn't really control for that. So that was our initial assumption. Again, can't really do anything about it at that point, but it's important to recognize that limitation and the assumption that we make and document that, right? You'll see this throughout the presentation about me trying to highlight the importance of us as data scientists being intentional about the choices we make and documenting those choices, because those have real world implications. Okay, so we call this ML model or whatever that we build a prioritization support tool. That means we want to prioritize people for rental assistance. So we are supporting that prioritization, right? So it can be a machine learning model, that a fancy machine learning model does a prediction, or it could be some simple system as well, right? Whatever the model that we use is doing is we are taking everybody who's going through evictions now and putting them in a ranked list. And then we are taking the top, right? That's the goal. So ordinal list, going from a set to an ordinal list. So we tested a bunch of machine learning models. We typically, in any project, we typically do this. We go from simpler linear models to shallow decision trees, deep decision trees, go to ensemble models like random forests, boosting algorithms, extra trees, like all of those systems we typically try for every model, because machine learning models utility is contextual. Sometimes a simpler model is enough. We don't need to throw ensemble at it, right? And in addition, we also try simple heuristics. Another lesson, always try alternatives to machine learning, because machine learning systems are expensive to maintain and deploy. So if we can't do machine learning, what can we do? With the information that we have, can we do simple things that still improves the status quo and is cheaper to implement, simpler to understand, and easier to maintain, right? So a typical heuristic that we try is, can we use one or two indicators to rank people? Because we want a ranked list, right? So one of the things that we tried was, based on the number of times that you've been homeless in the past. So if you've been homeless multiple times, you would go on top of the list, so a higher risk, and go rank people by that. Another thing that we tried was ranking based on the recency of the most recent homelessness spell. How many days have elapsed since you were homeless last time? Does that make sense? And if it's like very soon, then you go to the top of the list, right? So like simple things like that. Other things that we tried were, can we rank based on the number of assistance services that you've received from the county in the past? That means if you interact with more services, that means you have higher needs. So maybe you are at a higher risk, right? That's the rationale. So all of these systems we tested out, and to have like no ambiguity on how this maps to the decision-making system. This might be a little redundant, but I'll quickly go through it. So we have everybody who's going through an eviction. Imagine your model is built, right? We send them through the model, and the model maps them to a ranked list. Top of the list is highest likelihood of interacting with a homelessness system. Lowest is the lowest likelihood of interacting with the homelessness system. And then we take the top K individuals and we do outreach and give them the intervention, This is the overall decision-making system. And K in this case is 100, right? So now we have this prioritization support tool. We've implemented a bunch of algorithms, bunch of machine learning algorithms, simple ranking systems. How should we go about evaluating this? Any metrics that we should use? Any ideas, thoughts? What is the metric that we should use to evaluate it? If it were up to you, what would you?
They went homeless or not. Again, after the help, if they either way went homeless or not.
So we're not acting on the model right now. We have a bunch of predictions. So let's say we have a score from first person to the last. Now we want to evaluate how good the machine learning model is. What metric would we use? Yes.
Probabilistic model, which one was more probable to don't have or be homeless in the study? Maybe you can get a probabilistic from machine learning.
We might not even need to go that low. So without thinking about like machine learning, if we think about what is a correct decision here, let's say we select K people. If yes, sorry, the one with the hand up, yeah.
The age of the people.
Age?
Age.
As in how old they are? Okay. How would that help us? Like, let's say I want to select whether I should use a machine learning model or a simple heuristic. And so I need a performance metric. So think of accuracy.
True positive.
True positives is one. Yes, exactly. And?
I think in this case, having a false positive.
Right. Okay. Right. Yeah. False positive rate. True positive rate. Precision and recall. Yeah. True positive rate is recall. So, okay. So, without even going to machine learning terms, so we select K people to give the intervention, right? If we want to use our resources efficiently, we said we don't want to give resources to people who don't need it. So we have to make sure that the K people that we give the resource to actually needs it, right? So that means if we didn't help them, they become homeless. Your point earlier, right? So efficient means out of the K people that we select for the intervention, about how many of them were we correct about? So how many of them were true positives? So that is not true positive rate per se, it's precision or positive predictive value, right? And we don't, so when we calculate precision of a model, what do? We take all the scores, we use 0.5 as a threshold. Anything above 0.5 is considered a predicted positive, anything below a 0.5 is considered a predictive negative, right? And then we calculate precision. If you use sklearn and do dot predict, that's what you get. You get a 1 or 0 as the output, which is unfortunately wrong because these are not probabilistic models. So using 0.5 as a threshold implicitly is incorrect. We get a score from 0 to 1. So for instance, the highest score that we got here for this model is 0.37. There's nothing above 0.5. The only utility of that score is to help us rank individuals, right? So using 0.5 blindly and discretizing the predictions is not adequate here. It's not adequate anywhere. But so what I would think of it as a score here, and we don't have to guess a threshold, right? A threshold is given to us by the use case. The threshold is 100 people. So we take the top 100 people, that is where we draw the line so that anything above that 100 people are predicted positives, anything below them are predicted negatives. So now we calculate our precision in that predicted positives. So we said 100 people are at risk. How many of them were actually at risk? That is a precision metric, right? And then we spoke about effectiveness. So effectiveness means an effective decision is there's this person who is actually at risk of homelessness. If we don't help, they become homeless. Now we help, they don't become homeless, right? That's an effective, so we flip that outcome. Unfortunately, with observational data, it's very difficult to evaluate that. We will have to run an experiment, right? A randomized control trial to evaluate that. But as a proxy, we typically use true positive rate or recall to do that. So recall means out of the ones who actually needed the help in our population, how many did we actually end up helping, right? So there were, let's say, 70 people who became homeless out of that 4,000 eviction cases. Out of that 70, how many did we help? Which is recall, right? So, and we, or sensitivity, depending on which school you went to, right? So we always use this at K to signify that this is not an absolute metric. This is a metric calculated at this specific threshold. If you change K at 200, it's a different metric, right? So that's effectiveness. So recall is a proxy of effectiveness, not a real effectiveness measure. But if we reach everybody who needs help, then we are effective, right? Because we are going to help the people who would change the outcomes as well. Does that make sense? Please feel free to stop me and ask questions anytime. So that's effectiveness, efficiency. There was a third thing. What was that? Equity, yeah. Equity, right? Fairness. We care about, because these are people's lives. So we are affecting a direct outcome. We are informing a decision that directly impacts people's lives. So we have to be careful that we are not exacerbating. So we live in a biased world, right? And our decisions, our data comes from biased world. Our decisions can exacerbate those biases. This model is built from information gathered from a biased world. So we have to be careful of how this algorithm is impacting that communities that we want to take care of, right? Equitable resource allocation is the third thing that we want to care about. And we want to make sure, so we use this principle called equality of opportunity to calculate equity. That means, is our model more wrong about, disproportionately wrong about a specific group of people over others? So for instance, is our model performing worse for black individuals versus white individuals, right? So we use recall, group recall to evaluate that. So what that means is, let's say there are 40 individuals in the black community who end up homeless. There are 20 individuals in the white community that end up homeless. In our top 100, all that 20 from the white community is included, but only 20, so 20 from the white community is included, 20 from the black community is included. We are catering to similar white and black individuals, but our recalls are very different, right? Our recall for black individuals is 50%, our recall for white individuals is 100%. So we are helping everybody who needs help from the white community. We are only helping half the people who need the help from the black community. So is that fair or not? That's the conversation to be had, right? Yes.
Are there any other factors used for demographics besides ethnicity?
So we typically do gender as well. And in this use case, we did first-time homelessness versus repeat homelessness. We did very poorly on first-time homelessness, spoiler alert. So our models can't really predict effectively first-time homelessness. Like shocks to the system is something difficult to predict. It depends on the policy context. So race was, in the United States, unfortunately, a lot of the social services programs, race is a very relevant factor. In hiring, for instance, gender is a very relevant factor. Race is a relevant factor again. I'm trying to think of a policy context where race can be. Age is a relevant factor, yeah. So we don't have information, but household size could be a relevant factor, right? Like families with kids versus single individuals. Like, are there things that we need to think about? So like different aspects that we need to think about depending on the policy context or the problem context that you're dealing with, basically. Yeah. Any other questions?
How do you avoid this bias if the black population is, as you said, too much bigger than the white population? How do you prevent it?
Good question. Yeah. So the first step in preventing that is measuring that, right? The first step is to identify that there is a problem. So, and there are mitigation strategies that you can do to, so for instance, you can have different thresholds for different groups. So, and we call this like achieving recall parity, right? So if you want equalized recall for white individuals and black individuals, you can adjust the threshold that is used for black individuals to get selected for help, right? So, and we learned those thresholds from historical data. So we would lower the threshold for black individuals to come up the list. So then, and their threshold would be lower than white individuals, for instance. Or we expand. So it can be done in different ways. So let's say you're stuck with 100 people. We can only help 100 people. We are not bound to the machine learning gods to help the top 100 people, right? So we can select who to help. So we would select 30% of white individuals, 70% of black individuals, for instance. So we rank the two groups separately, and we select more from the black group to match, to balance the recall. Does that make sense? So we are kind of over-serving. I'm sorry.
How did you select this proportion?
So we learned that from historical data. So we know that, so I will get to like how we repeatedly build models and evaluate them over time. So the best we could do is we can learn those thresholds from using past data, because we have data for the last 10 years. So we'll try to learn that information from that and try to balance the thresholds, and we keep evaluating that. So do the intervention this month, we'll have to wait for another year, then evaluate whether our choices were correct, and then adjust. It's an iterative thing. Another thing we could do is, if you can find other resources, let's say you can help 130 people, right? So the other 30 resources we spend to balance in the equity. Your top 100 is your top 100, then the other 30 that we found the extra resources for goes to the underserved group. That's also a way of doing this. We call this like presenting policymakers like a menu of options. Okay, this model is going to be biased. These are 3 different ways you can think about mitigating those biases. And there are ways to do that, to mitigate this. These are like established practices that people use. Does that answer your question? Okay, so this comes to the, okay, now we have models, we have metrics. How do we evaluate how robust the models are, right? So anybody who's heard of k-fold cross-validation? Probably everybody, right? Like if you've studied machine learning, what do we do? Why do we do k-fold cross-validation? Anyone?
One thing is to avoid bias, so you split it on test and string. So you avoid bias. Part of avoiding bias will be
Yeah, exactly. Bias, not from a societal sense, but from like model being biased sense. Yeah. Okay, and you mentioned to prevent overfitting, right? Because if we do only one, if you train and test only once, there's a risk of it being a fluke. So your model is great at this one test set that you had. So you are very happy, you deploy it, and somehow that fluke is not there anymore, that your deployment performance is really bad, right? So that in that scenario is like called overfitting. So you overfit to that particular training data, which is not representative of the general use case. So in k-fold cross-validation, what you do is you split your data into equal k folds randomly. Let's say 5 folds. You train with 4, test with 1, right? And you repeatedly do that 5 times. So your model is basically, so you have, if it's a random forest with 10,000 trees, your random forest with 10,000 trees is tested 5 times on 5 different data sets. So if the model performance is kind of consistent across those 5, you make a claim that, okay, this will generalize into the deployment context. If we do that here, any risks that, would that work here, this context? If we randomly split the data that we have, let's say we have data going back to 2012, we randomly split data into train and test. Yes. Okay, we have to stratify across time. Okay, that's one. Okay.
Yeah, I was going to say the same thing, that you have to take into consideration that you don't know what's going to happen in the future. So you kind of make the crossfold across time. So you get like the beginning of the time, and then you test with the next cluster, just to say, but then on the next k-fold,
Right.
you test with just what you know from the past, and you test, train with what you know on the past and
Test on the future. Yes, exactly. Right? Because if we randomly split the data, let's say we have data going back to 2012, let's say every year is a fold. So we test with 2013, but we train with 2015 and 2016, then we are leaking information from the future into the train set, right? Like that doesn't work. So we have to take temporal constraints is a big thing. So k-fold cross-validation very rarely works in the real world because there is time involved in a lot of applications. So randomly, like naively splitting data randomly, more often than not introduces leakage into the system. So try to avoid that and think about it. So we'll go through the example, exactly what she kind of proposed. Let's say we have data until 2024, 01, 01. So label is a span of 12 months, right? Whether someone interacts with the homelessness system within 12 months. So the first analysis date that we can have is 2023 January 1st. Does that make sense? Right? Because we need 12 months to observe the outcome, right? So that's the first analysis date that we can have. That's the first eviction cohort that we can take. Everybody who was going through evictions at that time, January 1st, 2023. And then that is your validation cohort, right? That's your validation split. How do you train? We have to go back another year, right? To observe training labels. So now your latest train date can only be 2022 January 1st, correct? And it's difficult to train with just one cohort and test with one cohort. We need more data to train the model. So we stack multiple train cohorts on top of each other. So how the matrix gets created is you take cohorts from January 1st, 17, January 1st, 18, and you just stack on top of each other and you have this long matrix of individuals. So each person is represented at a specific point in time. And in practice, our models were, I'm just doing this for illustrative purposes in yearly cadence, but in our models, we did it every 4 months. So for every 4 months, we took individuals who were going through evictions, had an eviction filing in the last 4 months. That's our cohort. And next 4 months, the next evictions cases that were filed in the next 4 months, and we stack them on top of each other. And that's our training cohort. And the validation cohort comes a year after the training cohort. Any questions on this? That clear? Okay. And then we repeatedly do this multiple times, right? We did it, I think in our model, we did it 25 times. So we had 25 folds of this. For illustration, I'm only showing 3. So we go, so this is the top one is the last validation cohort that we can have, and we work backwards, right? So, and what we end up with is results like this. Yes?
Did you make changes to the model in some steps that you mentioned? Did you notice something
What do you mean?
models. But when you test the model
Mhm.
in your evictions, did you notice that they were needed some changes or some?
So what we test there is whether our model is robust across time. So we take same model and run it for all folds, and we end up with something like this. So each point you see is a validation fold. So if I can go up here, so like this is a validation fold, this is a validation fold, this is a validation fold, this is a validation fold. So this random forest model is instantiated 1, 2, 3, 4, 5, like I think like 20 something times. And we ideally we want to see is like how does it variate over time. This box you see here over here is the pandemic. During the pandemic, evictions cases kind of disappeared. Our cohort is eviction cases, so we don't have a cohort, right? So the model is kind of irrelevant at that stage, so that's why we don't consider that. And now for each model that we try, we have this line. So random forest, I'm not showing all the lines here. Random forest has a line. The orange line is a logistic regression. The third one is a heuristic. I mentioned the days since last homelessness spell. How many days have elapsed since the last time you were homeless? That ranking model is the green line, and red line is a random selection. That's the base rate, basically. So about 2% of the evictions cohort end up homeless. If you serve people randomly, you're going to be correct 2% of the time, right? What can you gain from this, basically? Which model would you choose if you had to?
Heuristic is easier to maintain, and it's almost like logistic regression.
Okay, he will use the heuristic.
Yeah, random forest.
Random forest. Any other ideas?
In terms of cost efficiency, the days is last.
Days since last homelessness, the heuristic. Is it more clear when I speak from here? Interesting. So yes, there's cases to be made to everything, right? Let's take the heuristic. What is the risk of using the heuristic? Yes, the efficiency is correct. Who would we ignore? What about people who've never been homeless before? Would they ever be in the top? No, right? But maybe there is an allocation for that, right? Maybe we use this heuristic for people who've been homeless before, and because we know from the data that people who haven't been homeless before, maybe we do something else. That's a very valid, viable way to operate if the maintaining and deploying the machine learning model is too costly, right? You can say so.
Did you use this heuristic metric as a feature in the random forest model?
Yes, it did. Yeah, we did. Actually, how we ended up with this heuristic was the most important feature in the random forest model, right? And that's also a trick, right? If your random forest model has a very important feature, if it's easily calculable, if it is easily calculable, right? Use that as a ranker and see how well it does if you only have that.
You can keep your feature selection the top 3 and make it a new heuristic combination.
Yes, exactly. You could do that as well. It didn't change much. I think we tried like a rule-based type stuff with this. It's been a while. I don't remember the exacts, but so this was the best heuristic we could see. Logistic regression model is the best linear model that we could see. Another thing here is, should we select models only based on this? What do you think? Would I ask that question if it was a yes?
You mentioned before, I think it's important to consider maintenance costs.
Maintenance costs. And we were thinking of 3 goals, right? Efficiency. This is efficiency. This is the precision metric, right? Equity, right? We need to look at equity as well, right? So effectiveness is recall. If precision is higher, recall is going to be higher here, right? But it will be interesting to see how equitable these models are in terms of decision making systems, right? This is a plot that we use to gauge relative equity versus efficiency. So this x-axis you can see is the effect, like the efficiency metric, precision. The y-axis you can see is the bias metric, which is recall ratio. So just focus on this plot over here. It's unfortunately not super clear here, but this is a bias ratio. So for race, for instance, what we do is we have a reference group and a protected group. So for instance, in this case, the protected group is black individuals or black families. The reference group is white individuals. So if we are serving them equally in terms of recall, their recall ratio is 1, right? We call that perfect parity. So this line is that recall ratio is 1. We are serving them kind of equally based on the need. Anything above this is we are missing fewer black people who need the services. Anything below this, we are missing fewer white individuals. Does that make sense? So I think it's easier to think of from a false negative rate rather than a true positive rate. Think of, are we disproportionately missing people who actually need the help from a certain group or not? If your false negative rate parity is 1, then that means we are missing people, we are equally wrong when we are wrong, right? So if we are above this line, we are more wrong about white people. If we are below this line, we are more wrong about black people, right? So equity here, is it parity or over-serving black individuals? What do you think? There's no right answer here, but one could argue that black individuals have been historically disadvantaged when it comes to housing, and they're disproportionately impacted by housing issues. So their homelessness rates are much higher than homelessness rates of white individuals. So we need to try and get down the homelessness rate of black individuals at a faster rate than we try to get down white, because at least we can either we can get them down at the same level, or we can get black individuals rates higher and then get it to the same level as white people at least. So if from that angle, you could say that over-serving black individuals is more fair in this case because of the historical context, right? And if you look at our models, all our models kind of are over-serving black individuals. And we had a conversation with our partner, they were fine with that, right? Because they are disproportionately impacted by homelessness, black individuals. So where we want to be ideally is to this side of the plot, where predictive performance is higher, and where you want to be in terms of bias. So if you want parity along this band, if you want over-serving along this band, if you want underserving over here, right? So this is something, sorry. Sorry. And so this was the plot for race. This was for gender. Same principle. Here the protected group is women. Reference group is men. So if we think about false negative rates again, rather than true positive rates, we are less wrong about women on this area of the plot. We are less wrong about men in this area. Here we are kind of equal, right? So if we look at the dots here, the ranker, heuristic, unfortunately I didn't match the colors from that plot to this one, sorry about that. So the purple is over-serving women and over-serving black individuals, right? And less performant on average. I think this model, this average value doesn't exclude the COVID dates. That's why the numbers are kind of different. But ignore that for now. So this model we selected, the random forest one, is the more performant, right? It's over-serving black individuals, but not at the rate of logistic regression. It's 1.7, close to 2 times more recall for black individuals, and it's kind of parity in terms of gender, right? So that's the model that we kind of went with. Yes. We didn't look at intersectional biases, but yeah, that's a good point. We've been meaning to do that for several projects. We've only been looking at like single attributes. How to look at like intersectional attributes, we haven't done that before, but that'll be an interesting thing to look at. Black men are disproportionately impacted, just looking at historical data, but haven't looked at the black women's rate. At least I can't remember this one. Yeah. So this is an example of how we can present results to a policy partner, right? So earlier we said, so this axis, this plot that you see, ignore the table for now. This plot that you can see this is the list size. So list is like 100 was the list size earlier. So we expand the list size to like 2000, right? What would happen to the two metrics that we care about when we change the list size? That's what you see. The red line you see is recall or sensitivity or true positive rate. The blue line is the precision or positive predictive value, right? As expected, the lower down the list we go, precision drops, but recall increases. This is also a plot you can use to debug your models. Just a hint. Once you build a model, just create this plot, check for two things. Your recall should end at 1, right? If you're including everybody in the predicted positive class, your recall should be 1, and your precision should go down to the base rate at the end. So if those two things don't happen, then there's something wrong. And if the recall curve is like a random line, like a straight line, that means your model is not doing anything. It's just randomly picking things, right? So those three things are good sanity checks whenever you build a model. Just a digression. So we check 3 thresholds. 100, the original one, right? So for the top 100 list, we found that 27% of that, so that means 27 people were people who are going to actually become homeless. And recall is 24 for that, right? But if we expand our list to 200, our recall goes up to 37%. But if we can help 500 people, we can help 60% of the people who need the help, right? This is the menu that we show the government agency. So one thing is that they haven't thought about what is the programmatic impacts of getting more funds, right? So now this is a use case that they can take to a funding partner, right? Like the state government or the federal government who's giving out the rental assistance fund to say, hey, if you give us enough money to serve 500 people, we'll be stopping 60% of people who are becoming homeless, right? Like that's a good tangible policy use case that they can use. This is one example of like how to convert your metrics that we calculate using sklearn to actually impact and inform policy, right? And this would be even in a company, right? Like where you are trying to allocate resources for optimizing anything, like at different thresholds, what are the impacts of your decisions? What are the impacts of these different levels of resources? At the company, it might be the dollar revenue or anything else metric that they care about. Here, the metric that we care about is homelessness rates, how much we can impact that. One interesting finding we had was, so they have the current practice, right? That you can call and apply for rental assistance. So in our 2022 August cohort, out of like around 4,000 people, 111 ended up being homeless within a year after the eviction. 89 of that 111 never applied for assistance, right? That's an overwhelming percentage of people who end up becoming homeless don't even probably know that this help exists, right? So, and we checked whether our models actually discover that, a portion of those people. At list level 100, we discovered 26% of those people. List level 236, again, list level 500, 60% of those people would be discovered in our list. That's also a good use case for the policymaker to make. Hey, the current system you're doing, this could be a much better alternative to what you're doing today, right? You will be reaching the correct type of people. That's one way we try to reach to the partner. So this is the project. So the modeling of the project kind of stopped maybe like a year ago at this point, maybe even more, right? What we are working on now is, modeling is completed. So we've been building processes to fetch data at a regular cadence and refresh the data sets so that we can keep producing predictions, right? So like working towards the deployment case. So generating predictions is all fine, but we are the ones who have access to that predictions in our database. But the people who are making the calls and doing outreach are completely separate. How do we get these scores to them? This became a total nightmare, right? This was something that we had not considered. We still don't, so it's been what, year and a half since we've tried to, maybe a year since we've tried to start doing this. We still don't have an optimal process. What we're doing right now is we are writing the scores to a spreadsheet every week. That spreadsheet gets updated to a Teams folder. And it's not even the county who's doing the outreach. There are two nonprofits who are doing this. The nonprofit agency takes that spreadsheet, makes the calls, writes the notes on the spreadsheet, and we have a script that takes that spreadsheet, writes those notes back into a database, right? And every week, so it's a new list, right? And that's sometimes the people that we give them in the previous list, they don't have time to get through everybody. So there's people left in the previous list. Now, do we append to that list the same spreadsheet or put a new spreadsheet, right? It ended up being a new spreadsheet. And you can't programmatically write things to Teams. Now, what we are doing is we are manually uploading an Excel file after we generate the Excel file programmatically and manually upload it. So it just became a huge pain, and it is a huge pain still. Yes.
And that could be like a survival analysis. So for people that you know that it's going to be evicted, see how long it's going to take them to be evicted. So you put the ones that are going to resist the most time in the end, so that maybe if they don't being called at this point in time, they are at the beginning of the next list, because you know they are going to resist more than the ones at the top or something like that.
Right. It's the thing is, it's not the reason that they don't get through the list is not necessarily a function of the person that they're trying to reach, but other stuff that falls on the plate of that nonprofit. These are organizations who are like super spread thin, right? They're serving their communities on different housing elements, and this is one of the many things that they do. So some weeks they just don't get to the list. It's the harsh reality. And it's not like a thing that we can predict, like these people would be the hardest to reach, right? So that's where it's fine. We need to figure out like what's the optimal size of the list is, so that we don't overwhelm them with numbers. I think we are kind of settling at like 30 to 50 people. Seems like the best optimal set of people to give them to get through, right? But like this is something that has been, so what we do every week is, it's not me who's doing it. Again, I'm a foreign national, so I couldn't be contracted by the government because I was on a work visa. I couldn't have multiple jobs. I could only have one job. So I was already working for CMU. So they couldn't, even though it's not paid, they couldn't make me a contractor of the government. So I couldn't get access to the data system directly. My boss and Alice, my other colleague who's working on the project, she got access to it. So she has a county laptop. So she runs a script on the county laptop, on the county data warehouse to fetch the data, to run a bunch of Oracle scripts to fetch the data, to CSV files. Then we transfer those CSV files to our AWS cloud. Then write those CSV files to our Postgres database. Then we run the models on that, write the scores from the Postgres database to a spreadsheet, and then upload that spreadsheet. And every week it has to be a new spreadsheet, and there are 5 different outreach partners. And some outreach partners have sensitive information about some of the clients. For instance, child welfare services. So the reason there are multiple outreach partners is these individuals who are outreaching, we are reaching to, have other services that they receive. Rather than giving them a call, it makes sense to use the touch points of other services to talk to them, saying, hey, while they go into their child services check-in or whatever, say, hey, we saw that you're going through an eviction. This resource is available to you. You might be eligible. You should talk to these people, right? That type of outreach. So child services people have information about them that other people can't see. So it has to be separate lists and separate places. So Alice, unfortunately, alone, like updates 5 or 6 different spreadsheets every week. And that's how it's deployed right now. Sorry, you had a question.
Why you didn't use or create a custom application for that? You could create some roles or permission system to make it more secure, to make some automatizations to
Yeah.
to stop the whole process if you have a lot of things to do.
Right. Exactly. Right. Which we had started building that. Right. I'll get to some lessons learned sections. So, and the other things that we are working on is we are working with the data science teams over there to transfer the models to their data science team. And we've been thinking about whether this system works in addition to their current practice or as a replacement of their current practice. Because there's discussions about that and there are disagreements about that. If it's a replacement, that means they will have to say no to some people who call and apply. And people who take that phone call doesn't want to do that, right? It's an uncomfortable conversation to be had. Someone is calling me, asking for rental assistance. Hey, the model doesn't think that you're high risk enough, so we can't help you, right? That's brass tacks. But at the same time, they might be needing the resources less than other people. It's a limited resources we have to target. So that's a difficult conversation that's been going on.
Sorry, thanks, Sober.
Okay.
Possibly 2 questions.
Okay, sure. So I will quickly some lessons. Make sure to think through implementation details at the beginning of a project, right? That's one lesson that we learned. We didn't talk to the frontline workers on how to get the scores out to them. Had we spoken to them 2 years ago when the project started, we would have a system by now, right? The county could have built an app that gives them the scores and do that. Talk with the program leadership whether we can change eligibility criteria of the program. Currently, we can't. So even if we identify the people who need it the most, if they're not eligible, they're not going to get the money. So the model can be perfect, but it won't change anything, right? Talk with the program leadership to talk about like, how would we validate this? How would we run a field trial for this? If we want to run a field trial, we'll have to say no to some people who call. How would we handle those conversations? How would we tell them, how would we engage community to tell them, hey, we are testing this out. So that means we might have to say no to some people that call. How would we have those difficult conversations, right? So start collaborating with the tech team in that organization early so that we can transfer. We found out that they don't have compute like a couple of weeks ago. They run things on their laptops. How are they going to run this, right? So those conversations like basically is what I want to get to is outcomes that we want to impact is a function of an overall process. And a model is a significant, but only one part of that. So thinking through that entire decision-making process and bringing people into the fold early who are part of those decision-making systems and thinking of it holistically and making decisions is one lesson. If you don't remember anything from this talk, please remember that. Thank you. That's for me.
Bye.